In this video, we're going to take a look at Gibbs free energy and equilibrium. So the equilibrium constant K is related to the standard Gibbs free energy chain for a reaction by the following equation. So delta G equals negative RT ln K. So R is the universal gas constant, 8.31 joules per Kelvin mole. Temperature is T in Kelvin, and then ln of K is the natural log of the equilibrium constant K. This formula doesn't have to be memorized because it can be found in section 1 of the IB data booklet. So now let's work through an example. The equilibrium constant K for the following reaction has a value of 5.97 times 10 to the power of 5 at 298 Kelvin. So we're being asked to calculate the standard Gibbs free energy change for the reaction. So this reaction is the formation of ammonia from nitrogen and hydrogen. So let's solve. So delta G equals negative RT ln K. So that is equal to negative 8.31 times 298 Kelvin times ln of 5.97 times 10 to the power of 5. That equals negative 32,935 joules per mole. But remember, we need to convert to kilojoules, so it's negative 32.9 kilojoules per mole. So in this example, our reaction is spontaneous because we have a negative delta G. So let's look at some values comparing delta G and K. So here are 4 reactions, and here are the delta G's and the K values. And you'll notice that the more negative the delta G value, the larger the equilibrium constant. That means that the more spontaneous the reaction, because negative delta G's are spontaneous, the more the equilibrium will rush to the right, going further to completion. So when you look at these values down here, we have really large K values, and there's a larger negative delta G. So more spontaneous, more likely to favor the products and going to completion. So now we'll take a look at the relationship between the equilibrium constant K, delta G, and the position of equilibrium. So we'll look at delta G, the ln K is there, and then the equilibrium constant. So if delta G is negative, the ln of K will be positive, the equilibrium constant will be greater than 1. So the equilibrium will lie to the right, favoring the products. If delta G is 0 and the ln of K is 0, Kc will equal 1. So you'll have equal proportion of reactants and products. And then if delta G is positive, the ln of K is negative, the equilibrium constant will be less than 1, so it will lie to the left, favoring the reactants instead. So let's just analyze this graph. This is a graph of a spontaneous reaction of the Gibbs free energy and the progress of the reaction. We took it from the Cognity textbook. So in this example, the Gibbs free energy decreases until it reaches a minimum point, and that minimum value will be at equilibrium. And this value is also equivalent to the maximum entropy of the reaction. So for spontaneous reactions, the position of equilibrium will lie towards the product side, as you can see. This is a graph of a non-spontaneous reaction, so you can see that Gibbs free energy decreases until it reaches a minimum value, which is at equilibrium, but it's lying on the reactant side, and then it increases. So this value is also equivalent to the maximum entropy of the reaction. And for spontaneous reactions, the position of equilibrium, that minimum delta G, is at the reactant side.